Right, so guys, what we're looking at here is rates of reaction, and I'm continuing on from yesterday. Now, we had just gotten to the point here where we had talked about a rate of reaction being where we're looking at the speed of the reaction, or you might say the amount of, we'll say, a product that's being produced per unit time, or the amount of, we'll say, reactants that has decreased over per unit time. So, really, there are five different things that we think about when we think about changing the rate of a chemical reaction. Okay, so you can substitute in the word speed if you're not very comfortable with the word rate, but really we're talking about changing the speed of the reaction. How do we do it? Well, the first thing is we change the particle size, and we talked about that yesterday. Concentration of the reactants. You could say the type of reactant that you're using. You could say the temperature, whether it's hot or cold, and you could choose to use a different type of catalyst to try to speed up that reaction. Now, what I'm going to do now is I'm going to go through each one of those in a bit of more detail so that we'll understand where this is all coming from. So, the particle size. I want you to imagine the experiment you just did at home, where you looked at a tablet and the rate of a reaction when you added that tablet to water. Imagine you had a whole tablet and compare that to a tablet that had been broken up into, we'll say, a quarters, or maybe it was broken up into eighths. Which of those reactions is more likely to occur more quickly? And probably your hypothesis straight away would be the ones that the tablet that was broken up, because the particles in this case have a larger surface area to work on. So if we're talking about dissolving, we'll say, a tablet into water, what would happen here is that it would dissolve much more quickly because the particle sizes here, there's a much greater chance that the water will get in between the tablet broken parts so that it can dissolve. So this, I suppose, rule applies almost across the board in science. The greater the surface area, the greater the speed of the chemical reaction. And we know this to be true when we are cooking as well. So if you're cooking, for example, a potato, and I gave you this example yesterday, compare when you're cooking a whole potato versus a potato that has been cut up into smaller bits. We know that the smaller bits will cook more quickly. And the reason for that is because there's a much greater surface area. So the rule of thumb in science, the greater the surface area, the greater the speed of the chemical reaction. And this explains things like biochemical reactions in our body as well. Like, for example, in our mouth, when we consume food, the first thing we do is we try to break it up with our teeth so that we increase the surface area so that enzymes can work more efficiently. So that is the first one, which is particle size. The second one is concentration. And when we're talking about concentration, really what we're talking about is the reactants. Remember, the reactants are the chemicals that chemically react together. So say, for example, yesterday we looked at iron and oxide, or iron and oxygen rather. Iron and oxygen react together and they produce iron oxide, which is a scientific name for rust. When reactants react together, the more concentrated the different types of reactants, of course, the faster the chemical reaction is going to happen. So if I have, for example, a lot of iron, and I'm going to give it a higher percentage of oxygen. Atmospheric oxygen is about 21%, but I'm going to pretend now that I'm giving it a concentration of 50%. I'm making it artificial, and I'm going to put oxygen in with iron so that iron reacts with oxygen. What I should find is that there will be a much faster chemical reaction because the iron will have reacted with the oxygen more quickly, and therefore more iron oxide will have been produced. So as time continues, what we could say is that the concentration of the product will go up and the reactants will be used up. So concentration is of course a factor. You can think about that as well, like when you're, for example, dissolving in, we'll say, sugar in water. If I have more water, we'll say, a larger amount of solvent, and of course the sugar will dissolve more quickly. than if I had a tiny amount of water and I had a large amount of sugar and I just plopped the sugar in. It's not all going to dissolve that quickly. But if I have a large amount of water, in other words, a high concentration of water, then the reaction between sugar and water will happen more quickly. The reactants have a certain nature, and on the periodic table, sure, we know this quite well because on the periodic table we know that certain elements react more, I suppose, quickly than others. So if we look at the periodic table, for example, I'm just going to bring up a picture here. So we know that, for example, the alkali metals, which are the ones in the group 1, on the column group 1, they have only one electron on their outer orbit, which means that they are very, very reactive. And so if I take, for example, let's look at lithium. Lithium would be much more reactive than, we'll say, other like types of metals, because it is, like, say, for example, lithium here would be much more reactive than a non-metal like, for example, helium or neon, because this has one electron in its outer orbit, whereas these guys here have a full outer orbit. They cannot take any more electrons. So the type of chemical or the type of element makes a big difference. I don't want you to get bogged down in these words here, ionic compounds or covalent compounds. Just know that where you are on the periodic table may make a difference. The next thing then is the temperature. So temperature here has a bearing, because the higher the temperature, what it does is it increases what we call kinetic energy. Now, you remember kinetic energy from second year, because kinetic energy is basically the amount of movement of the particles. So all the ways back in first year, we said, hey, there's such a thing called matter. Hey, these matter, what they do is they vibrate. And as you heat them up, they vibrate more quickly. Well, if you can imagine, if these particles are vibrating more and more quickly as a result of being heated up, then they're going to hit each other more often. And that's going to increase the likelihood of a chemical reaction happening more quickly. So that's why, as we increase the temperature of water, for example, that sugar will dissolve into it more quickly, because the particles are vibrating and they're much more likely to come in contact with sugar particles more quickly. So it's explained here in what we call effective collisions. There's more collisions. The more collisions you have, the more product you form more quickly. So general rule of thumb is, as you increase temperature, most chemical reactions will occur more efficiently. So when we talk about increasing temperature, really what you're increasing is heat. So that's why what we do with the kettle is we pop on the kettle nice and hot, and then we add in the sugar, because we know that the sugar will dissolve if we're trying to make, for example, some hot chocolate or maybe some tea. Right. So we'll be looking at this energy profile. So I'm not going to look at this in detail at all, but I just want to finish up here on number 5, which is the catalysts. So certain chemical reactions will happen much more quickly based on the presence of what we call a catalyst. There is such a thing as a biological catalyst in science, and they are basically another word for enzymes. So enzymes in our body, we know that chemical reactions would not be quick enough to happen if it wasn't for enzymes being present. Like, for example, inside in our mouth, starch is broken down to maltose. That's a chemical reaction where starch is broken down to maltose, and it's caused by the presence of amylase, salivary amylase, which is in our mouth. So a catalyst will speed up that chemical reaction. And when we say an enzyme has been catalyzed, we mean that it has been sped up. And what effectively an enzyme does is it reduces the amount of energy required for the chemical reaction to happen. So this here, EA, would be what we call the original chemical reaction without the enzyme. And the red here, in this case, is called the catalyzed reaction. It has It's been sped up by a enzyme. In fact, inside in our body, the speed of breaking down many of the foods without enzymes would be you'd be talking about thousands of years rather than doing it in seconds. And that's because catalysts reduce, like enzymes, reduce the amount of energy required to start that chemical reaction. Now, what we want to do now, and I'm going to skip away from biochemical reactions, I am going to ask you to um, look down here. What I'm going to ask you to do actually is we'll answer a few questions from the book, and I will pop this up in Google Classroom, and you will put them into assignments for me. So we'll talk to you later.